Hello, gentle readers. Reading Foundations today from a study with Ross Finlayson here in the state of Idaho, United States, across the river from a great hillside of trees, which are notably absent the snow that usually covers this part of the world for months at a time every year. The seasonal temperature is remarkably unseasonal, 30 degrees above average, which isn't so bad in the time of year when it otherwise just involves shoveling the snow every day and these kinds of things. Yet it is bad to consider that adding 10 or 15 degrees in the summertime just results the conditions untenable for the well-established ecosystems of the things. But that's a global phenomenon that everybody's sort of dealing with and coping with, that all our copers need to be incorporated these kinds of ways. So in reading foundations today, that being the weather, then and the otherwise the usual ideas and things discussed here with regards to the theory and both the pure and the applied, or the practical of the theory, and the comprehensive and thorough accounts of the theory of everything. And so that's just usual. And there's a couple hundred hours more of these kind of video essays that would be a little bit more perhaps in the narrative, in the stream, in the linear, as of an account of the stream of consciousness of sorts. That is an extemporaneous account, an unscripted account, and otherwise, as for helping to relay what may be some perceived value from somebody who, as a researcher in foundations, is able to provide as a sort of, how one might say, seasoned, experienced account of the thought processes involved in these matters. Reading is fundamental. So today then, well, what I have been leafing through a little bit here is a book by O.W. Richardson, a Nobel Prize winning physicist, about 100 years ago or a bit more, having written this book, The Electron Theory of Matter, helps to make the great sort of bridge between the electricians of the 19th century, kind of as with regards to Faraday and Compton and Coulomb, as after Ampere, and then it's about Heaviside and FitzGerald and Larmor, and a bunch of different sort of accounts of the theory of electricity and the theory of magnetism and the theory of electromagnetism, as what results from Maxwell's laws. E cross B, how about D cross H? Or vice versa, which one is it? Either way, it's just kind of as for the crossing of the field lines of the changes in the electric fields and the magnetic fields. That here, that's also with regards to the electromotive and then displacement current, 3 or 4 different kinds of current that today is almost entirely described as Maxwell law for Kirchhoff and circuits, as for Lienard-Wiechert potentials of electron holes describing current as defined in amperes. So the notion of the waves here is kind of reflected for Faraday and Faraday rotation as of the spiral waves and wave spirals. So that the usual account of the wave as a model of an open system is sort of accommodated by a space-filling continuous spiral as the mother of all waves and the father of all waves. For the wavelet theory, or Ondelet's with regards to the wave theory, or On's. So Richardson's book here, it gives a great detailed didactic account of the formalisms involved in the theory which arrives, including the infinitesimal analysis, which is basically shows like for 2 charged bodies, when they coincide or when they begin to diverge at the edges there, that these are accounts usually ignored and simply not part of the mental model of a particle theory as for Pauli principle, that no two particles are combined, and that they are distinct, that they are as of mathematical points, yet that is not exactly in this particle conceit. The idea that the working model, a mental abstraction, quite a bit of the reduction of otherwise these complex and comprehensive continuous things as didactic and discrete and the less difficult things. That Richardson's theory then helps to explore that then as for the other great confluence about energy, and that with regards to that being related to special relativity, the theory, where general relativity, the theory is just like there is no absolute motion. Motion is relative. Space is absolute. Time is absolute. Motion is relative. It's kind of just the lever to give a point of perspective and projection. Then is with regards to that, then it's like, and it's classical on the limit with regards to Newton's laws, and Einstein's attack and defense on Newton. Then that special relativity is just like, and light speed is a constant. And then for after mass energy equivalency for FitzGeraldian account mostly, but all these different F-Lorentzians, their fields, their accounts of the Lorentzian after the Galilean, the how one might say space contraction, that variously gets split out as length contraction and time dilation, because the pieces fall apart of each of these partial accounts after the Laplacians, after the Lorentzians. The sum of second order partials of three orthogonal dimensions, which then is with regards to that making a corner of a box, is also kind of like not having the other corner of the box. The Laplacians and these, with regards to the usual account and the usual formalism, that Richardson then helps show that there are at least three constants C, which are given like usually for matters of mass energy equivalency, that is just defined as light speed. It's defined, not derived, but actually derived from electromagnetic theory and derived from the electrostatic theory. According to Richardson's account here, there are at least three constants C, and they differ. They're like one slightly greater than light speed is usually given, and one slightly less. And then that gets into why, with regards to wave mechanics, that for electromagnetic waves and current and radio and waves of radio in the electromagnetic spectrum, that's wave velocity more so than like the actual velocity of a beam or ray of light. Here that it's pretty well explored that electromagnetic radiation both has high and low frequency components for flow and flux, and that optical light is special and only really coincides with the electromagnetic radiation is about frequency and wavelength, defining energy. So it's only about energy, and then as regards to the resonances, of course, to that relating color in spectrum, that being its own sort of thing, and with regards to various forms of the emission of light and the theory thereof, that Richardson provides formalisms from which it can be derived. That then these different means of the legs of the empirical triangle that actually hold up all the practical fields of physics that are let out after the simplest models after Maxwell's law for Ohm and Kirchhoff and the like. That and there are other ways as well that can be shown, like Lienard-Wiechert for his theory of potentials, since, for example, the Laplacian let out as the Laplacians being zero or harmonic functions, and that's potential theory is incomplete. That overall it helps show that Richardson book provides promontory, meaning standing kind of on its own account book, the electron theory of matter, that both kind of funnels it into the reduction, yet also is having come from a place that is able to pick up and carry the empirical aspects to relevant. That otherwise reductionist accounts that don't carry the intuition and its own constructive inductive accounts that it has as to so follow would get an incomplete, say, with regards otherwise to the course. So that's kind of what I've been leafing through here, and I read it quite a bit over some time, and then it also helps to talk about like Poisson, and how that's relevant to the Gaussian and all the things that end up for Green's theorem and for Stokes and what's called advanced calculus, and the terms about grad and nabla and del in the cross product in the vector algebras that is so bog standard that everybody who's ever sat through college physics curriculum has gone through those, has sat through those derivations. One hopes. All right, well then here's the new box of books, or the old box of books. Oh, okay, great. And the first book, and this is a book I got about 25 years ago. It's Schaum's Outlines on Tensor Calculus. So when I was trying to, before I had really sat the rest of a physics curriculum, I was still trying to learn everything about it and want to know everything about it. So when I started to study relativity theory, it's like, I was like, well, I know vectors. What is this here? And it's like, well, it's tensors. I'm like, well, how is tensors different in vectors? It's like, well, it doesn't really say. And the reason it doesn't really say is they aren't really different. Because tensors eventually presume to preserve tensorial products, just like vectors. Their idea is, as they live in their space, they preserve vectorial products. So the tensors is preserving tensorial products have, for example, that vector is a perfectly good tensor. And then with regards to things like the Euclidean and non-Euclidean, that's matters of perspective and projection. And so then the tensors basically just say, for something in his, if I would paraphrase someone who's trying to think like Einstein, say, I might say this like, well, it's a tensor formalism because between this metric over here, which is finds distance for the Lorentzian, dx squared plus dy squared plus dz squared minus dt squared equals ds squared, or, you know, flipping the sign about that on both sides, plus minus that. The sign conventions and these kinds of things, that it's really just a matter of like, well, according to our conformal geometry and affine geometry, that would have to add back up, but according to that, that's a very tough thing to figure out, and why we have Riemannian geometry and Lobachevsky geometry. Kind of Riemannian geometry is like, it's a gravity well, it's space-time is just, that's the well in the middle, and Lobachevsky geometry is like, well, that's where it lets out on all the edges, you know, but it's still Euclidean geometry everywhere. Basically, the vectorial is Euclidean, and then the tensorial is just to make for the accounts of Riemannian and the Lobachevskian, say that's pretty comprehensive of the most inner products and the outer products. Why then tensor development isn't that big of a deal. So for when they call it coordinate free then and these kinds of things, like, well, how is it coordinate free? It's like, oh, you have to build your own coordinates. It's coordinate free. I'm not going to say, I don't know, but you're going to have to do it yourself and build these things to keep it real. It's like, so in this formalism, all you're saying is that it's got to add back up, and then you have a perfect formula. It's like, yeah, that's pretty much it. You know, and then I just kind of got like this in the gravitational field equations. I just kind of got like 8 for like 2 cubed in the quadrature, and bring that down and over a square root of that, and then these are these components, and then it's just according to these coefficients, the subscripts on the tensor components, as of those basically being lines or areas in a volume. And what's the other great thing about this tensor calculus notation? It's like, oh, well, there's just a convention that there's a summation convention. So when you see ijk, we're just going to write it as I. So all this is saying is that this little expression in like the GUV or whatever, and the 8G and this under the root is just the last thing that results in the middle, kind of like square root of 2, vis-a-vis square root of 2 over 2. So familiar in all sorts of trigonometric identities, and you know, root 3 over 2. That this it has it then that then the convention for the summation convention, or Einstein summation convention, is just saying, oh, well, that's just bracketed out and brought back in however it so happens because it's Lorentzian. So that's kind of account that's a brief kind of summary of what it is and what it does. And this gets into all the stuff that it was so much to learn and to absorb and that is in the middle of all this derivation. This was a wonderful book, and I felt like it really opened the world to me to get into this field of study, because this kind of stuff, and it's often laid out in a course. This is a sort of condensed variety of this kind of thing. With regards to the quadratic forms for a covariant affine tensor, giving an example of after transformations in the orthogonal, it just shows then for the transpose of these tensors as of their conventions, the relations for about the symmetrical and about the transpose, and here about the convolutional mostly vis-a-vis the linear plainly, and these kinds of things. Permutation symbols in the Kronecker delta. So the permutations of Kronecker delta is like, and it's all going to be computed in matrix mathematics, matrix multiplication. By matrix, meaning a two-dimensional matrix, vis-a-vis like a grid or an n-dimensional matrix or something like that. These are almost completely and always just plain old matrices. If you want an account that's more after the Cartanian and geometric algebras or the hypercomplex numbers, with those being sorts tuples and expressions, the coefficients whose products are guaranteed fall within various ways of preserving the transformations, that again, all this that goes into the tensorial is just to preserve the products and making for keeping things according to the triangle inequality or Cauchy-Schwarz, and then that there's about the metric and norm, because that's the only way to really say, and it's the only thing that the existence of a metric really says for the metric and norm, length and distance, then those being the same somehow after the coordinate free, after the tensorial products, back into vector products, and the Galilean and the Cartesian, which everybody knows so well, the number line, then the diagram of a plane, or r squared and r cubed, regards to the usual notions of vector spaces, and the linear. That this is a pretty cool account. And then the Kronecker delta is just an example of something that's like, well, it's like an identity line. So when we can drop it out and you can find out if the matrix is singular, then all these different things about eigenfunctions, and then solving, getting that up back into relating that to the Hamiltonians, which are just systems for the eigenfunction approaches, like functions, matching those out is what make for those can be canceled algebraically. And then the numbers will compute and kind of spin around the dial of matrix multiplication to keep these things so that they have what results addition formula of vectors, which is what it does graphically. That this is a great account, and it gets in a bunch of different things. It gives a bunch of exercises. Establish the familiar identity for the vector product of three vectors. U cross the quantity v cross w equals UWV minus UVW. So for the cross product and then the vector products, or in coordinate form, the EIJK UJ of this quantity, EKRS URWS equals the quantity UJWJ times this quantity VI minus UJVJWI. And that involves, it can involve a number of different ways to kind of start getting into what makes for an associative law and the distributive law, and then how that works to make an addition formula, in this case, a subtraction formula, and is about those being balanced and not, and the ideas of these sorts of derivations that follow. That would probably help to revisit a lot of the little derivations as from vector addition and addition formula, and then for things like subtraction formula, and all such notions of the usual accounts of those as related on the hinge of Eulerian-Gaussian screw arithmetic and the e to the I pi, or to the Cartanian and reflections and rotations, or just to plain an account of the original and the identity itself. There are lots of different ways to establish these things to follow that just ends up that it results that there are straight lines, right angles, and 1.0 metric and norm, and the Cauchy-Schwarz. That's what these things arrive at, because then they can say, thusly our stack of cards is square. the quadratic. Because then up to first order, all the terms that live in first order get eliminated by second order decimation, in a sense, for an account of decimation as mathematical. And then that everything above third order is undefined, and that's the way it is. It's simple. Rules for absolute differentiation: sum, outer product, inner product. Christoffel symbols of the first kind. So Christoffel, as all the Christoffel and Schlaefli help introduce crystallography classes and symmetries. And so often it's as for the cubics and the rhombics and the notions of, before getting into the cylindrical and these kinds of ideas, that for all the and the hexagonal and those kinds of ideas, that for all the issues involved with packings of regular polygons and polyhedras in areas and volumes, and then so that for all these boundaries, just like that's what we started with, is an integer lattice on the plane, and these are square here, and so it's the same approach with then the Christoffel and Schlaefli. So then the tensors live in these classes of these sorts of approaches, and so then the end of it, it just like looks like a normal algebraic expression. Yet it's just having kind of that's like its reduced form, way reduced. And so the relations so follow, the implicits and all the derivations are always still in effect. If they're so implicit, and that's the reductionism for you. And then when it comes out that that's having lost things when it was partial, and then it's incomplete. It gets the incomplete again. And then it gives, for example, symbols of various kinds. So there's Christoffel symbols of the first kind and Christoffel symbols of the second kind. Kind of like Stirling numbers of the first kind and Stirling numbers of the second kind. Later, they'd be ascribed as like Stirling cycle numbers. It's after Pascal and choice numbers, or Bernoulli. How many given this are like those from combinatorics. And then for the subset numbers, it's like, well, how many subsets can you make? How many permutations can you make? They're given more descriptive terms. But then as they're first kind of explored, it's just kind of general categories, kind of like studying Kodaira the other day, and all these different approaches of the complex analyticity, and where it fails, then it gets in like, well, there's kinds, there's or classes of these things, and those are qualitative first, and then to later become descriptive, as then with regards to, according to the algebras and the derivations so possible to see hold for these things, that they're like so. So tensors, and getting into this then brings a lot of the gamut of different kinds of ideas, as after plainly addition formula, when you can result taking two terms and they result one term, and vis-a-vis plain cancellation, which is you can take two like terms and consider them the same. So then for subtraction formula, when you just like, it's kind of like an addition formula, but it makes a zero, so it's also just happens to coincide if analyticity holds up. Does that being a root for polynomials and these kinds of things? For the elementary functions, trigonometric functions, polynomials, their solutions, roots, radicals, that being about it. Then as for accounts for when getting into, after the fundamental theorems of algebra and the fundamental theorems of arithmetic about the existence of real roots of polynomials with integer coefficients, and with regards to the unique prime factorization of integers, those being the fundamental theorems that those exist, that then the accounts for Ruffini and Abel, it's like, well, where in elementary functions can these be solved? Then as for things like, well, if you just add something like Lambert's W function, and then you get into a lot more to do with pi and phi, and those being rational, and for like Apries numbers and Lambert's W to be considered an elementary function. otherwise that they're special functions, or that being basically the difference between elementary and special in the account of functions that result all the roots and radicals for all matters of algebra in all sorts of usual derivations of piece. That this is an example of bringing all these different things together. And then for things like Bessel functions and all their various kinds. The Ricci tensor. So the Ricci tensor is basically, the idea is like, well, yeah, after Toledo Levi-Civita, and that there is an absolute differential calculus, and yeah, we're thinking about the indefiniteness of ds squared, this discrete quadratic square element, ds squared. That the Ricci tensor is like straight line, bisects the right angle. That's kind of the idea here. Let's see. A brief look will be given a tensor that is of importance in relativity. The Ricci tensor of the first kind is defined as a contraction of the Riemann tensor of the second kind. So it involves a paired up subtraction formulas to result in expression for, if not zero, then just the Ricci tensor itself. So it basically just gives, for an addition, says, okay, the Ricci tensor is the leftover part of that. If it's non-zero. And then in relativity theory today, you'd relate in a high level, Ricci and the Regge map being kind of like the inner product and the outer product, and the Bianchi and Baecklund. It's like, how about least symmetries and the ideas of that and the convolutive, and then Bianchi and the identities, and then Baecklund and as of the symmetries. So Ricci and Regge and RACCI and REGGE and Bianchi and Baecklund, BIANCHI and BA umlaut CKLUND. So, and that's just that's something that here it was read a long time ago about Mogan and the nonlinear effects and applications. And so these kinds of accounts that build this in relativity theory can be taken away from that and just used just because they have accounts of addition and subtraction formula in these terms and these forms about the definiteness and indefiniteness of the implicits, the explicits, and all these definitions and derivations, that Mogan makes an account for the surface acoustic wave transducer that is true and is used to solve for things like today. That's a most usual account of simulated quantum computing. That this sort of grab bag assortment of derivations can be used in all kinds and sorts of different ways. Then in the piecewise, it's kind of broken out that way. It's like Kodaira will say, hey, well, let's see, who is that? Hilbert and Banach. You know, it's like, well, you're kind of done there in terms of the analyticity, according to the partials, held up great until there was, anything that spins 360 degrees. So now we got to make this sort of account of, what is actually implementing this tensor calculus to keep it tensorial. And I'm just going to, it's like Lescope puts it, it's like just take a section and make it piecewise. And then where the fringes of the edges can still kind of be said to not waver too much, then we'll have an entirely different kind of like a singular integral or accounts for algebraic geometry, more the geometric approach than the algebraic approach. So this mentions a lot of things. This mentions the Langlans program. It's incomplete. Well, how about the Langlans geometric program? Well, they say that's very difficult because it would be complete. And these kinds of things. For a geometrization is kind of above an algebraizations and arithmetizations. What's the fundamental theorem of geometry? World measure. It's his name, is the idea. Here there's an account overall of function theory as measure theory as kind of like the loosest moving parts of analysis. See, here's a calculus or physics textbook, Serway and Jewett, 6th edition. So this wasn't the one I used in school, but it's one I picked up one day because it's a great sort of physics book. I had one of my uncles, he taught AP physics and chemistry. And then, and I'm not sure which, and then I have his text from when he was in college. Just as an example of these things. So I don't believe this is the one that we used in school, but perhaps it was. And it's got like a bunch of problems. And usually people aren't made to do all the problems, but there are a few every week or so. A 15.0 milliwatt helium neon laser, lambda equals 632.8 nanometers, so visible. Well, it's about 660, so it's emits a beam of circular cross section with a diameter of 2 millimeters. So it's an area. A, find the maximum electric field in the beam, Z. B, what total energy is contained in a 1.00 meter length of the beam? And C, find the momentum carried by a 1.00 meter length of the beam. See, the total energy is over time, is kind of what I'm thinking about. So it's a volumetric term described as like then an energy, a particle is dimensionless. And so then trying to figure out is like, well, how many photons is that? Is if we're going to say, and then what about that being a laser? And what about that being, according to the stimulated emission of radiation? And like the design of the cavity, figuring that most lasers have are cavity resonators. That then resonation it makes constructive interference of waves is the usual idea. And so how can that be figured to be like a uniform current? And then to then compute off of those terms essentially, it's like, well, the electrons have this kind of wavelength, and there's so much electron according to the flux here. How bright it is. It just it says 15.0 milliwatt. So yeah, it's a 15.0 milliwatt. It gives how much is in it. Then the idea about these kinds of things in flow and flux is this. So when trying to figure out flow, it's fluid models, and then flux is the idea of, well, it's what's left over, and so then flow in liquids is like, well, or gases, it's like, well, it hangs up on the edges, but flow in electricity is like it goes fastest at the edges. This is the core effect and the skin effect, two things that make electricity in its model of current and liquid in its model of current as entirely opposite, yet otherwise sharing all the same thing, which regards to the potential differences and why they're considered to be the same with regards to the fluid models of things, and as with regards to wave mechanics is about the continuity relations and continuity conditions and continuity equations. So the idea is this, is that any kind of, it's considered as just like adiabatic, and so it's always just like a heat, it's just going forward. But really it's constantly wavering on its way out. There's ripples and eddies and the idea of turbulence all the way. So then the idea is to figure out something like pulsed, the resonator makes pulses, and then that makes for vortex rings. And so then in this manner, it's possible to describe, well, you get the spiral waves and wave spirals into the account. And so then it makes for helping to explain why these equations, a lot like Heaviside's equation and the telegrapher's equation, and why his account worked to make a transatlantic cable when the one that came off otherwise, the derivation out of Maxwell, failed, is the accounts in the empirical of matters of flow. It's like, well, how does the long stream, it kind of runs fast, and then when it gets to like smooth and deep running, or when it gets to slow and meandering running, while it's still in the same course. The idea is to embody that as magmas, these vortex rings, where magmas is kind of like the lava lamp idea, and it's also related to algebras, that algebras generically are called magmas. But these magmas of flow dynamics help explain that that's not particularly relevant to helping to compute. Is like, well, how much energy is in that laser? For example, when we put in this many milliwatts, and then how deep a hole will it drill in this metal plate or something like that, or how many cats fall in the red dot will it blind or something silly like that, which is often introduced as a sort of way to maintain a curiosity into a problem, and as well an abstraction from the problems and these kinds of things. That's a very common sort of account for all kinds of things, and that pulsed light or laser light is different than unstimulated emission radiation. There's a great YouTube channel called Huygens Optics, and it helps cover some of these ideas. There's a great YouTube channel about the supercontinuum. Good TA, teacher's assistant or something like that, gets into these ideas about the optics. And the pulsed power, where pulsed power is delivery of impulses vis-a-vis constant load and these kinds of things. That such an example toy problem as this, the Gedanken, the Zonsen, the setup, the problem, the experiment, helps show that then, just like in the considerations that laser light is pulse power and vis-a-vis the continuous wave and these kinds of things, it's involved, near field, far field, and all this kind of stuff. That then the electricity is sort of that radio is also like so. The design and model of an antenna is that there are deeper currents in the electrical too. And so again, for optical light and electromagnetic radiation being different, while still having the same models of the equations of energy in the areas, and for the flow and the flux, that defining then the model of the fluid and the various models of the fluid, this deconstructive account and why it adds up back classical in the middle, like zero, is great. It's great. So that, yeah, what I had been thinking about over the past couple weeks is that I'd like to introduce this idea of the vortex rings as with regards to the adiabatic and non-adiabatic, and why so many accounts of the empirical were great on paper with ideal components, the ideal components vis-a-vis the practical components in the empirical, that they don't agree, is for making is like, well, they can agree. Concepts of probability theory. Pfeiffer, McGraw-Hill series, and probability and statistics. So this would be probability theory. Ex libris. Probability theory. Here it's, and this is from 1965. So probability theory and statistics theory gets involved with limit theorems of probability and time, chance, and uncertainty with regards to statistics. There are at least three of those apiece, and the usual theory has one. And so there are others. Just like there are three laws of large numbers, there are three continuous domains, each apiece, different. Three Cantor spaces, they're models. One rather Pythagorean, one rather Cantorian, one right down the middle. These are things. Integral of a simple random variable. So sum's an integral. So first it starts with random variables and probability distributions, and so the continuous and the discrete of those being different, and then for probability functions and these sorts of things, random variables and events. So this would be considered kind of above a usual course called college statistics, and right before a usual college course called probability theory, and kind of helping to bridge it. Probability theory refers to the occurrence of events and their accidents, their occurrence and their accidents. So not just what occurs, but when it occurs. The Search for Freedom and the Next Generation of Man, The Quantum Brain, by Jeffrey Satinover, Satinover. Do we have free will, or just imagine that we do? If you imagine that you do, then why not? There are lots of accounts that be like, there are lots of accounts just like the account of like, well, they took a boat and then piece by piece they replaced every single piece of it. Yet at any given time, it was kind of assembled as, it had a name. Is it the same boat? Yeah. Just water under the bridge. The Search for Freedom, the Next Generation of Man. 2001. Wiley Inner Science, I think it said here. Let's see. The Quantum Brain, John Wiley and Sons. Okay. Mind Out of Matter, Opening the Mind's Eye, these being the names of chapters. Death and Birth, Teaching a Young Dog Old Tricks. The Wet Net, so wetware, the brain. Spinning the Glass, Fantastic. Miracles, that's part 2. Fickle Chance and Chaos Judge the Strife. Quantum Ripples. So we've got a section, the last chapter has a section on free will. So let's see what might agree with it. Magic Pyramids. So here I'd mentioned with regards to models of fluid and flow, there's the magic triangles or magic squares, or Latin squares. They add up and all the different rows and columns to be the same. So it's like, well, that's just like if it was uniform. If you sum over all the possible ones of those, yet it still affects or reflect. Those can be positive and negative and reflect the waveringness of the waves. The idea of the wave is the wave front, the crest, the element that moves. Here these magic pyramids. Then let's see, magic pyramids is talking about models of orbitals, bonds, and atoms and molecules, or atomicules. And then they're just minima and maxima defined by geometric relations like crystal classes and stuff like that. But then looking to this section about free will, it's under let's see, religion and belief, the future, free will. Majority of scientists, especially those who study the brain, consider the question of whose will not worthy of asking, let alone answering. Nonetheless, the fact that the entire operation of the human brain is underpinned by quantum uncertainty and the likelihood that the brain is structured so as to make actual large-scale outcomes mechanically indeterminate casts a new light on the question. So that seems agreeable, because and it still makes an account that there's individual accountability and this responsibility. So yes, I don't automatically throw this away. Satinover is a practicing psychiatrist, past president of the C.G. Jung Foundation, and a former fellow in psychiatry and child psychiatry at Yale. And he says he has been a William James lecturer in psychology and religion at Harvard. He's currently a special student at Yale. And so that sounds great, except about William James, it's like it reminds me of the era of the 1910s and 1920s in America. And so James was about education and psychology or psychiatry, and it kind of reminds me of Dewey, not Melville Dewey or whoever who's for the library system, but John Dewey, the prolific author and philosopher about these things. That I appreciate Dewey after James as being progressive in a sense of being open-minded, but then he's kind of completely swallows the Kool-Aid and is like, my open mind now is a closed mind. It's like, well, that's one of the problems that accounts that logicist positivism tricks itself with inductive ignorance and invincible ignorance. And so it's solid, that sort of position, but I don't buy it. So yeah, I'm not a fan of James, although this is being a common name, but James, like the school of James and Dewey, that's just not so relevant here. Third edition, Fundamentals of Digital Logic and Microcomputer Design by M. Rafikuzaman. 1632 and 64 microprocessors. associated logic, daisy chain interrupts. I'm going to be looking at this because I've been planning ideas about how to understand how to write an operating system for computers. So that's rather ambitious, isn't it? Well, the idea is that the general purpose programmable logic device has a model of microcode and then firmware and then software. And how it's afforded to be configurable, programmable, is with the notion that there's a clock chip to like drive and run a program, and then with regards to being able to respond to events, there are the interrupts. So the interrupt is usually a verb. In English, you'd say interruption as an event of an occurrence of something that was interrupted. But an interrupt is a signal, and in an instance, an event of a signal in a microprocessor. And so these basically are the events. And then the hardware and the software interrupts basically reflect the events as are hard-coded or hardwired. And then the events as are simulated or stimulated, synthesized to make for that they handle themselves in a model of handling events, which is fundamentally known as a loop. So modern processors today are the multi-core and many-core. And so it's been a long time since they first had is like, well, we're going to have single instruction, multiple data, or single instruction, multi-threading. And these kinds of notions of like, just some independent cores, please, or just the vector operations after the scalar operations, the superscalar operations. So the idea is that these days it's like, well, here's a chip fresh off the line. It's got 522 cores on it. Well, half of those are actually bad, but this way we can still sell you a chip with 256 cores on it because it makes them all the same, trying to make a perfect 512 core chip, but it's got out of it a 256 core chip. And so this is usual complex instruction set or reduced instruction set, but the usual notion of this CPU, the general purpose CPU then. And this isn't the same as when they talk about things like, well, how about a GPU, a graphics processing unit? And it's like, you mean a GPU, a general purpose graphics processing unit, where it's just got like single instruction multi-threading, 256 or 512 wide, that it just does, it can only run tiny little programs, but it'll split them up and do all those at the same time in kind of one unified pipeline that they're just stepwise pipelines together where these cores are essentially independent then about their proximity and their coherency and their domains and their regions as they are proximity, coherency, and affinity. So the entire chip these days is already a model of a distributed system all on a chip. And then the model of signals is as of interrupts. And so when thinking about trying to write an operating system, you already have to kind of design a complete network in a box if it's not just going to be a single top-down executive. To be a scheduler and a cooperative scheduler gets involved in these sorts of things. So by just flipping in the middle of this book and seeing it like, yes, these are the ideas and considerations and surrounds, and here's a logic diagram that shows for a verifiable synthesis that this is the standard sort of logic that can make a circuit in silico, in the silicon, kind of like in vitro, in vivo, in silico, that this is it. Resistance, capacitance, inductance circuits. It all works out to these in these pieces that come back together. Talking about the triple nickel or 555, a very common integrated circuit that's used to establish the timing of events for scheduled events. About the operating system is of the executive and the scheduler. And about events, the order of events, network theory, and traffic in events. Since that these days, a commodity, general purpose computer is a whole network in a box. Can operate in massively parallel, according to a little bit beyond the usual idea of the GPU or whatever in the embarrassingly parallel. Hydrodynamics by Sir Horace Lamb. Quote, has long been the chief storehouse of information of all workers in hydrodynamics, according to Nature. The Dover reprint, a wonderful remark. Dover has really helped keep a lot of important works in print. Horace Lamb, April 1932. This may be regarded as the sixth edition of a treatise on the mathematical theory of the motion of fluids, published in 1879. Subsequent editions, largely remodeled and extended, have appeared under the present title. So today, there's been consideration of like the model of fluids. So there's a model like pneuma and the models of gas, and then there's the fluids and the model of fluids. And one has like basically the ideal gas law, and the other one has the incompressibility and sort of just one step different from that of the entirely rigid, and kinetics and kinematics is of the rigid. So these also happen to correspond to the states of matter, and then plasma is just given as what is furthermore is of the superfluid and these kinds of things. So, given that this is an account is after 1879 and is still kind of in print today, one imagines that it will discuss Green's theorem and then Stokes' theorem, because that's so critical to what later became, after the Eulerian and Gaussian, for matters of stress and strain and tensors, the notions of Navier-Stokes and the fluid mechanics or hydrodynamics. But then another account of things when we talk about water, particularly hydrodynamics, is that will involve current in the usual account and static pressure. So static pressure is kind of like quite a complementary thing that's different than just usual notions of pressure and flow, because it's usually combinations of media, like a colloidal suspension or colloid, like a mountain of earth with properties of both kinetic and as of the water and of the humus of this terrain, the static hydraulics and hydrodynamics. Then it also relates to mention from O.W. Richardson when kind of starting this conversation, that it's also for that electricity has that as well. So for things like the electrostatic and potentials. There's a lot about potential series. So one imagines that this book might cover both the classical and linear account and then also be talking about potentials and potential theory. The subject, Lamb says, has in recent years received considerable developments in the theory of the tides, for instance, and various directions bearing on the problems of aeronautics. And it's interesting to note that the classical hydrodynamics, often referred to with a shade of depreciation, is here found to have a widening field of practical applications. Owing to the elaborate nature of some of these researches, it has not always been possible to fit an adequate account of them into the frame of this book, but attempts have occasionally been made to give some indication of the more important results and of the methods employed. As in previous editions, pains have been taken to make due acknowledgments of authorities in the footnotes, but it appears necessary to add that the original proofs have often been considerably modified in the text. Let's see, 10 chapters. Oh, he talks about Helmholtz. He's got Helmholtz and Kelvin. Persistence of vortices. Oh, this is great. Oh, this is fantastic, because this has a lot of accounts that have been lost and are just simply ignored or just never even mentioned in the usual account. I'm gonna put this next to Richardson here. I'm gonna read this somewhere later. The Geometry of Physics, an introduction by Frankel. So as we started today looking at that tensor book, this is that again. It's squared. And so it comes into, and then here's a model, for example, it's like, well, it's a diagram of a capacitor. So we're talking about this box and this square, and then this field, and then according to these two poles of this in the area right here, in a world where everything is all over the place, what's going on right here? So that's the diagram, and this is the cover of this book, and underneath a vector, say, is like this is a line with the arrow at the end of it. It's a vector. It always points somewhere. These kinds of things. This book is intended to provide a working knowledge of those parts of exterior differential forms, differential geometry, algebraic and differential topology, Lie groups, vector bundles, and Chern forms that are essential for a deeper understanding of both classical and modern physics and engineering, including our discussions of analytical and fluid dynamics, electromagnetism in flat and curved space, thermodynamics, elasticity theory, the geometry and topology of Kirchhoff's electric circuit laws, soap films, special and general relativity, the Dirac operator and spinners, and gauge fields, including Yang-Mills, the Aharonov-Bohm effect, Berry phase, and instanton winding numbers. Before discussing abstract notions of differential geometry, geometric intuition is developed through a rather extensive introduction to the study of surfaces in ordinary space. Consequently, the book should be of interest also to mathematics students. This book will be useful to graduate and advanced undergraduate students of physics, engineering, and mathematics. It can be used as a course text or for self-study. So to mention differential geometry, and the idea is like, well, what's differential geometry? It's like, oh, well, you like functional analysis, and then you want to actually get somewhere with that. So how about we just kind of cut off half of it, and you only look one way, and then that way there's a bunch of things to be solved. So when the author kind of says, it's like there's more around that, Well, at the same time, it's like we can use that directly. That seems that's for mathematicians, say. So tensors is section 2.4 after the tangent bundle, cotangent bundle, and phase space. So that's the model of like ordinates and abscisses, the tangents and subtangents, normals and subnormals, from like these books on vector analysis and introduction to a university course in vector analysis of continuous things. Okay, and then after tensors, he gets right to the exterior algebra, exterior differentiation, pullbacks, orientation and pseudoforms, interior products, and vector analysis. Lots of different ways. He's like, we can now make the convolutive out of that. There is a way back. We can make it back because because it goes there. These kinds of things. That section 1 is manifolds and vector fields, then tensors and exterior forms. 3 is integration of differential forms. So here that's considered with regards to the differ integro and the integro differ. It's like you differentiated it. Well, it's like, well, integrate that again. It's like, well, I kind of lost how it's integrated when the way it was differentiated, or vice versa. Or if I hadn't, then for you to kind of gloss that over naively is kind of like making a blocks out of Play-Doh or something like that. Looking for a kind of a metaphor, meaning that it's incomplete. The idea of that an integral is a function of a function, but a derivative is, well, it's an expression still of a function. The derivative is still a function of a function. And then it happens to also be intentionally and extensionally only that, but also that it's extensionally a number, like a scalar or a quantity. Or it makes for the here that would be for the account from the integro differ and different integro. Why integration of differential forms is more than just like adding and subtracting, because they have outsides vis-a-vis just the number line, whose only outside is plus minus infinity. The Lie derivative, Sophus Lie, is like, we'll make a setting for the symmetrical and convolutional setting. Holonomic and non-holonomic constraints. So that gets into like, where's our analyticity hold? When are we going to have to call Kodaira? Geometry and topology, covariant differentiation and curvature. So, relativity is issues. Relativity, tensors, and curvature. Synge's theorem. Now, that reminds me of, instead of like Singer and stuff like that, there's Synge. And so, for Ricci and Regge and Bianchi and Baecklund, maybe it's for something like Singer and Synge. S-Y-N-G-E. Talking about arc length. So that relate to like Jordan measure. Betty numbers into Rahm's theorem. So that's here. It's for more of an algebraic geometries approach as of Hodge dual. Harmonic forms Hodge, then Hodge. Yeah. Lie groups, bundles, and Chern forms. So that's number theoretic as Chern forms. That's combinatorics. They have kinds, say. Vector bundles. Here we kind of point to like Hermann and jet bundles and vector bundles. It's like, how do we make sheaves of these? How do they form a vector bundle is like a vector of a bundle. Just like a vector field is like it's an infinite dimensional vector, one field kind of thing. Matters of perspective and projection, and the holonomic, back to the holonomic and holomorphic, how that keeps things in perspective. Fiber bundles, Gauss-Bonnet, and topological quantization. Oh, well, that's great. It's like, and then now we can actually start computing some stuff. I mean, for physicists to get where they can shut up and compute, they had to scribble and think a lot. Well, good general readers, so hope Earthlings that as 2026 is underway, that good things. Good luck. So long.